Well, thank you very much. Yes, my name is Carlos Viana. I'm the co-founder of Photonics, and I'm very pleased to be here, having this opportunity to share some inputs about photonics packaging and about our activities, how we address these challenges. So the title of this talk is On-Chip 3D Polymer Microoptics. For different applications such as ultra-fast optics, fiber communication, sensing, and free space applications. I'd like to start this presentation by showing a bit the market needs in terms of photonics packaging. As you can see here, on the left, I'd like to enlighten this diagram, which is targeting the short and long reach photodiodes, where you can see in this axis the data rates as compared to the chip active diameters. So you shrink, you reduce the diameter and you increase the data rates of the device. So you can see here the diameters that are shrink down and make it faster chips. Finding here today's limit, which is 32 microns for the datacom detectors, top limit detectors, and 12 microns for the telecom indium phosphide based detectors. So as you increase the data rates, you shrink down the active areas, but you also make it more difficult to couple the light. So coupling complexity increases, which is the same to say that the test and assembly cost also increases. So talking here is the focus is about the active component. So on the right, we are more about the packaging overview. And we have this interesting paper published in 2016, which provides package cost breakdown to highlight where is the source of cost of these components, individual components. And you can see that the package test and assembly is the main source of cost. Of course, as we decrease the active areas, that means that assembly, the alignment will be more complex, and we will increase more this assembly cost. So basically, the main idea here is that the market needs to simplify the packaging solutions, to shrink down the active areas and speed up the alignments, and also speed up the alignment and also the speed of the chips. Now I'd like to give you a kind of technology, the coupling technology status overview, where in the left you can see a panel of different existing technologies, from the bud coupling, classic, discrete lenses, microarrays, to photon polarization, and also backside lenses. So different technologies with different advantages, different disadvantages. And on the right, there is the key challenges that we need to answer: the performance, reliability, packaging, and also the production capability. In terms of performance, how can we shrink down the active areas and make it still enough coupling? How can we relax the alignment tolerances, make it passive alignment possible? The reliability in terms of temperature, aging, vibration possible. Packaging compatibility, easy of assembly, compatible with existing packaging and assembly processes, and as well the mass production capability. That means on wafer production and integration possibilities, keeping the yield necessary for the industry demands. So with these two first slides, I hope I try to expose here the photonics packaging key challenges and give you an overview of the needs for the future. Now I'd like to introduce Photonics and try to show you how our solutions may be answering all of these key challenges. Photonics is a technological company created in 2018, growing team with 10 members with a great expertise on integrated polymer microoptics and microfabrication. Our offices and clean rooms facilities are based in France, east of Paris region, and we are a spin-off from a CNRS research center. We have more than 10 years of experience of this technology. You can see here the 650 state-of-the-art clean rooms production lines platform, but more than the infrastructure, we have access to a great experienced team on micro and nanotechnology. And this is a kind of our vision is to be inspired by this collective manufacturing process at wafer level using micro and nanotechnologies to apply it to the photonics packaging challenges. I'm just quite glad to announce you that Photonics is laureate of iLab 2020, which is a kind of prestigious French national innovation competition, and where we were on the top 10 companies of this competition. Let me now talk about the technology that we propose, the solutions that we propose, which is on-chip, wafer level, integrated micro-optics solutions. So we can see here in green the thin 3D microstructured polymer film, where in the middle we will find the core structure, which is tapered waveguide. Maybe here is better to see, where the geometry will be adapting the core, the fiber core diameter to the such smaller devices. And we have here this anchoring system that is connected to the taper by these suspended arms that will not influence on the coupling, which only gives us mechanical stability of this vertical taper waveguide. Three main benefits. First is to allow to shrink down the active areas, make it higher speed devices possible, keeping alignment easier. That means that we are kind of enlarging the effective area of the devices, making the passive alignment possible. The second is the custom-made solutions that we are applicable with photodetectors, VCSELs, LEDs, and PICs. Different applications we are targeting: datacom, telecom, quantum, and sensing applications. The final point is about industrial compatibility. Maybe some of you are thinking how we make these structures. Is it nano imprinting? No. So this is a monolithic integration process done at the wafer level using lithography. So this is a cost-effective mass production solution. And since we are applying it at wafer level before dicing the chip, we are transforming a chip to a pre-coupled chip, let's say. But it can also be a key point for wafer level testing, since we are applying millions of integrated tapered waveguides that will make it easier, the alignment and the testing of such many devices that we can find in the wafer. Let me go a bit deeper on each of these add values. The first, the performances. I like to highlight here. The first use case is a single mode to 10 micron detector coupling at 1550 nanometers, where we have the coupling efficiency compared to the fiber alignment position compared to butt coupling on red and green, the current technology. So you can see that the funnel structure will allow to collect more light and also make it enlarge the effective area of the device and make it easier the alignment coupling alignment. On the right, you can see here the different use cases: a 14 gig multi-mode VCSEL to multi-mode fiber coupling at 850 nanometers. We have here optical power of the VCSEL compared to the as a function of the bias and current. You see, as you increase the bias and current, the coupling of butt coupling decreases because we are exciting more modes, higher modes, so we have more losses. And you can see that icon technology in green will confine the modes inside this tapered waveguide and make it less sensitive to the excitation of higher modes of the VCSEL. Now let me talk about a bit more some designs and the possibility to customize the design. take into account different packaging and assembly constraints of our customers. You can see here, the main core is, of course, is the taper in the middle. And then the anchoring system, we will design it different, like pillars, like different aspects, in order to fit the constraints in terms of packaging, die attach, wire bonding, fiber attachment of our customers. And then the final final point is about the wafer level capabilities, as we apply it directly at the wafer in a monolithic integrated way. So we have millions of devices in a single process. That's why I was talking about wafer level testing that could be also a very excellent solution. I'd like to spend some time now on reliability and robustness, since it's a kind of key point on polymer microoptics. I like to highlight because some of you may have that question, and I'd like to spend some time. I think it's important since it's been a kind of important development in terms of polymer materials, and I think it's important to highlight the different aspects here. So you can see here the different tests that have been done from classic Dalcordia aspects in terms of temperature cycling, moisture, shear stress, grading, temperature, stability. Even we are trying now to push it forward to cryogenic conditions, as well as for spatial space applications, the performance in terms of coupling and alignment tolerances, and of course we also have tested the chip performance to be sure that is unchanged in terms of frequency, noise, motor behavior, etc. Now I'd like to show you a bit what this technology can do, opening a new era of possibilities in terms of advanced wafer level packaging or interconnect solutions. So you can see here that the on-chip polymer can be applied not only on the wafer but also on the chip. We are kind of flexible for that because we can use the silicon carrier wafer interposer, which is a wafer, can be a silicon wafer, for each silicon wafer, for instance, where we will etch doing dry reactive etching cavities where we'll place the chips arrays. Can have this kind of virtual wafer having tens of arrays, or they can be an entire wafer. And from there, we can apply our microoptics or the polymer microoptics directly off the chip and use these microoptics as an intermediate layer to bring out a silicon wafer fixture. As you can see here, we will do wafer bonding using the polymer microoptics as intermediate layer. And from here, we can also do dry reactive ion etching to do openings to bring the fiber down that will be auto-aligned to the device by using these integrated funnels that will absorb eventual errors that we can have between the fiber and the device. So I hope this slide is quite illustrating our vision that we have this great experience and know-how on collective MEMS manufacturing process, and we will apply it to photonics packaging, having these possibilities for advanced wafer level interconnect solutions. Let me now expose a bit our capabilities. That goes from the characterization, design and simulation aspects that you can see here on the left. Here we will measure it, the chip, understand the chip, understand the beam, understand the optical properties that we need, and design our structure here in green, our geometry needed to answer the needs of our customers. From here we go to the prototyping phase, producing these structures in the clean room, doing it wafer level or at chip level, as I showed you just before, and developing eventually advanced wafer packaging, as I showed you before as well, and also doing the reliability testing. Last step is the production, that we can do small series production in our clean rooms, and also give the possibility for mass production with the transfer possibilities directly to the foundries. I'd like to now conclude my presentation with this slide where I try to summarize a bit what Icon Photonics brings to the table. How can we help the photonics community in terms of bringing innovative coupling solutions? So you can see here the same diagram that I showed in the first slide, where we have the active areas that shrink down to make it higher data rates possible, coupling complexity that goes up. But the moment that we apply our on-chip tapered microoptics, we will enlarge the effective area diameter of the active device, so make it the coupling complexity stabilized and make it passive alignment possible. And so we open a possibilities not only in terms of increasing the data rates by shrinking down the device, but keeping the assembly cost, assembly packaging cost constant. Performances, reliability, and mass production capability. I think it is important, full on wafer production capability, since we apply directly to the chip. This is important also in terms of the compatibility with existing manufacturing lines, high process robustness near to 100% yield. So with this last slide, I'd like to thank you all for this time for me to expose our vision, and I'm open for any question. Thank you very much.
Well, thank you very much, Carlos, for that very nice video. I can see that you're online.
Yes.
There is a question that's come in that you may have read already in the chat, but I'll repeat it for the benefit of everyone. So it's from Myun Sik Kim, and he says, thanks for your talk. And then he says, wafer level means, ? Batch process, or still you need to write components one by 2 photon polymerization? What is the maximum wafer size that you can produce?
Indeed, thank you for the question. This is a batch process. We do it in a collective way. Regarding the wafer size, today we are working on 4-inch. We can also do 6-inch. So that's it, up to 6-inch.
Okay, thank you very much. I don't see any other questions. I have a little one. I mean, can you estimate in any sense the kind of cost improvements you might realize with your packaging approach? I mean, obviously the improvement in yield promises much.
Yes, this is an interesting question. It's quite large question regarding the different benefits that technology brings. There is the aspect of improving the coupling efficiency, enable smaller active devices, devices that did not exist in the market, and also when we increase the alignment, that means that it's faster alignment that you need, and you can use an equipment that is faster, make it, and when it's faster, time is money, so reduces the cost. To evaluate is a bit difficult because you need to take an example for a component, what is the dimension, what is the fiber, what is the application, to give you an answer with the number that what is the amount of time that we win with this technology. We have done some analysis in terms of bringing a passive versus active alignment solution, and we estimate more than 40% cost reduction by decreasing the time of alignment using this technology.
That's great, thank you for that. I realize that's a difficult question to answer, putting quantitative numbers, but thank you for that. There appears to be a second question, although I'm struggling to see it. Is that Emma, can you help me here? I can see that you've mentioned a second question, but I can't actually see it. I'm afraid I'm struggling, folks. So I can see No, I think maybe it's just a repetition. Sorry, I think it's the same question
Okay.
as far as I can tell. So let me just check there was something else that came in. Just a moment.
Maybe I did not answer correctly, so don't hesitate to write me a mail or some.
Oh, there is something coming from Michael Levy. I think he's saying which foundries are supported.
So today we work with the foundries of the CNRS lab here in Paris. We have our own facilities, so we do our own production in our facilities. We can give access if we have a high volume demand. Since we use classic collective process, it can be transferred to any foundry because we are using classic lithography processes, using a stepper, using a contact master liner. So we are compatible with the standard foundries that we have in a different industry in photonics. So we have two steps. One step is to use our facilities where we do the design and prototyping, and we can go up to the small series production. And then, of course, if a small production is enough, we can use our facilities, or if there is a demand for mass production, then there is a possibility to transfer it to the foundries.
Okay, thank you, Carlos. And Michael's responded by saying, great answer, thank you. So we're spot on time. So I think I'm going to thank Carlos and indeed all the panelists and speakers and say thank you very much.